So this video is going to discuss why three-phase systems are so practical. So here I have an inductor, and this is just a single phase system. So we're going to start out with looking at a single phase system, and the way we actually generate alternating current electricity is by taking and using some sort of mechanical force to rotate a magnet. And so we have this magnet. As this magnet rotates around, when the North Pole is perpendicular to our coil, that's going to generate our maximum sine wave. Alright, so we're going to start off here actually, say, with the magnet this way, and so it's really not generating any electricity. So our sine wave is starting at 0, and then as it rotates around 90 degrees, right, so if once we're 90 degrees here, that gives us the peak of our sine wave, and then we drop back down to 0, and then we go negative when the South Pole reaches this side, then that would be our minimum peak value, and then we're going to return to 0. Okay, so that's how we're alternating. This magnet is rotating around, and as it rotates around, we get positive peak, and then we get the current flowing in the opposite or the negative direction as the South Pole comes around. So I just chose some easy numbers here. Right, so if we look at this, I have my current is going to flow through this top wire down through my load resistor and then return back to the coil. All right, and so we're going to, obviously we need the top wire to feed the current, and then the bottom wire to return the coil, and then of course when the magnet is rotated through the South Pole, the current goes in the opposite direction. But so to get the current to the load resistor, this 10 ohm load resistor, we need both the top wire and the bottom wire, because to have current flow you need a complete circuit. And so we already have two wires, and so let's look at how much power is being transferred. So obviously you can see here I chose the numbers very easily. Nice numbers here. So we have, using Ohm's law, we can calculate the current, assuming this was like an RMS voltage, we would have an RMS current of 10 volts divided by 10 ohms, right, which would just give us 1 ampere, right? And so we would have 1 amp of current. And so our power, right, power is volts times current. Okay, and of course there's the power factor cosine piece there, but I only have resistance here, so that's a cosine. The phase angle is just simply 0, so it's a cosine of 1. And so our power here is simply going to be 10 watts for this simple circuit. So now let's remove this bit. Okay. So now let's say that we wanted to double our power by feeding in another circuit. So let's say here that we have a second circuit, and these are both in phase. So both of these sine waves are we're generating the electricity, and they're actually completely in phase with each other. And so if that was the case, and let's say that they're out of phase. Okay, so they're out of phase. So this one has current flowing this way, and this one has current flowing this way. All right, so if we have 1 amp here, and these are 180 degrees out of phase, so the current is flowing here is 1 amp, then this wire here would have to be twice that. So it would actually have to be it would actually have 2 amperes of current flowing through this middle wire. And so remember, with copper wire or any type of wire, but as you run more current through it, right, you're going to need larger wire. So, you know, this center wire would have to be twice the size to handle, because it's handling twice the amount of current. All right. So, but by doing that now, we've doubled our power, right? So I had 10 watts in the top circuit, and I've got 10 watts in the bottom circuit, but I've got these wires here. So I've doubled my power, so I've got up to 20 watts now, because I'm running 2 circuits, but I have to have 3 wires, and this center wire would probably have to be larger, effectively twice as large as the other wires, which is going to, you know, cost more money, and it's going to weigh more, and things like that. So I've doubled my power. I added 1 extra wire, but then 1 larger wire here. Okay, so this is this would be for just 2 coils. So now let's take a look at having 3 coils. So if we had 3 coils, now if you look at a circle, okay, right, we know that a circle, when you start and you go around the circle, you have to travel 360 degrees to get back to the point that you started. All right, so if we're going to split this by 3, okay, then that would mean that we would want to put the coils 120 degrees apart so that they would be evenly spaced. So in a 3-phase system, we're going to separate them by 120 degrees. And so if we just hook up one of these to start with, right, so here is my 10 ohm resistor connected to this coil of 10 volts. And we know that this, of course, is going to be giving me 10 watts. So now what we'll do is we shall connect up a second circuit here. Okay, so we'll connect up this second circuit here, and it's not looking very pretty in this drawing here, but so here is my second circuit. and there's going to be a 10 ohm resistor here. Okay, and so that 10 ohm resistor is being fed by this 10 volt supply coming from this coil. And again, you know, inside of here, right, we would have this magnet would be rotating to generate these sine waves. And so we would have a second resistor, which would give us a second 10 watts. All right. But now, as I said, this is 120 degrees out of phase. And so the current, so when we have current flowing, okay, so when I have current flowing through here, when I have my maximum current flowing through here, and the maximum current flowing through this other one would be at a different time. So the maximum would not be occurring at the same time. So my copper wires, even though we're sharing this conductor here, the maximum current is not, the current between the two is not maximum at the exact same time, because the voltages are 120 degrees out of phase. Okay, so the voltages are 120 degrees out of phase, so the maximums are not occurring at the exact same time, so I don't need to double the size of the wire. I might have to have slightly larger wire than with a single phase, but not doubled. Alright, so now if we look at this, okay, so if we have this other one here, oops, that should be a resistor. So if we had a 10 ohm resistor here, so if we had a 10 ohm resistor here, I was drawing an extra wire there, but we don't need the extra wire. So now that right, if we have a 10 ohm resistor here for this coil, okay, we're going to have current flow through there, and then current's going to flow back through here, and I don't need an extra wire. I was trying to draw an extra wire there, but I don't need an extra wire. So here we have, going from our generated power to our load, we only have 3 wires. We only have 3 wires there, but we have 3 times the amount of power. We have 10 watts being used here. We have 10 watts being used here, and we have 10 watts being used here. I'm sorry, I've got an extra resistor here. This one doesn't. Kind of got carried away drawing resistors. This resistor doesn't need to be there. Okay, I already had that resistor. So I already had that resistor drawn right here. I don't know why I drew it a second time. Alright, so again, when we look at this, right, we have 3 wires. Okay, so in the first instance, remember up here in the first instance, for just one of these, to get 10 watts, I had this wire here, and I had this wire here, and I was getting 10 watts. Alright, and then I came in and I said, well, wait a minute, if we could add one more wire and one more coil and resistor, I can double my power. I can add this extra 10 watts and double my power to 20 watts, but I needed 3 wires to do that. Okay, so I'm doubling my power by adding an extra wire, and so that's beneficial. because I've doubled my power with one extra wire. But notice here, right, with that same one extra wire run, I can actually triple my power. So now I've got a total of 30 watts with just 3 wires. And so when you're talking about transmitting electricity hundreds or even thousands of miles away from where you're generating it, all right, you know you're going to need at least 2 wires, right? You're needing these 2 wires because the current has to flow down to the load and then return to the generation source. To have current, you need a complete circuit. So you need at least 2 wires. But by using 3 wires, we can actually transmit basically 3 times the amount of power. All right, so that is you know, for 1 extra wire, we can triple the amount of power that we can deliver. So that is very beneficial. Okay. Not only that, but when you look at actually the generating of it, right? If you just had a single, you know, if you just had 1 coil here, you know, usually actually they kind of double the coil up, kind of like this. Right, so when you have your magnet rotating here, okay, you have it injecting current here, and then on the opposite side, the south pole is injecting that current also, so it's kind of doubling the amount of current as opposed to if you just had a single coil like I have here, but they're wired so that they're adding together. All right, so that's one phase. And then, you know, we could come in here and again at 120 degrees now, we're going to put in the second phase. Okay. And then at minus 120 degrees, we would have the other coil going. And so as we're rotating around, we're getting these 3, and it's really hard to sketch this by hand, but as we're rotating this around, okay, we have the first sine wave, say, is our reference that's starting at 0. So we have this sine wave. And then at 120 degrees, now remember, this is 90, the peaks of the first sine wave are at 90 degrees. So we're looking at about 120 degrees. Okay, and this, so at 120 degrees, this next one starts going up. And then at 270 degrees, let's see, 90, 180, 270, not 270, let's see, 120 at 240 degrees. Okay, sorry about that. Yeah, so at 240 degrees, this one starts going up. All right, so usually, you know, so this would be 240 degrees. Okay, or minus 120. Okay, so this one is 120 degrees angle 0, meaning that it's crossing at time t equals 0, the sine wave is crossing. Then this one is crossing, actually this one is behind this one, so this one is crossing at minus 120 degrees, or if you went the other way, it'd be plus 240 degrees. But normally we like to keep the numbers under the 360, or under 180 actually, and so we use like minus 120 there. And then this one over here is actually at 120 degrees. So, oh, well, whatever the voltage, I'm writing 120 volts here. Whatever the voltage is, all three voltages would be generated at the same amount of voltage. But oops, this one would be at positive 120 degrees. And so what you're getting is you're getting the peaks these three different voltages being generated are being generated at 120 degrees apart. All right, and so that gives you a nice smooth flow. You can see peak, peak, peak. So you're always having one every 120 degrees. You're having one is peaking out from each other. So you kind of get this pulsating. Where with a ordinary sine wave, right, with a single phase, okay, here we have a peak, and then we have a negative peak. Going in the opposite direction, but we don't kind of have anything pushing positive over here. But over here, we always have one of the phases is kind of pushing along positive. All right. The other nice thing about that is for electric motors, okay, basically an electric motor converts electrical energy into mechanical energy, rotational energy. And so if you have a three-phase motor, it's basically the same as the three-phase generator I just drew. So we have like phase one, and then you have your second phase at like 120 degrees over here. And your third one at minus 120 degrees or 240 degrees. And so what happens then is these pulsating voltages generate a rotation. Okay, they actually generate a rotational magnetic field. So you have a magnetic field that is rotating around in this motor, and so that naturally forces the motor to turn. Okay, so a three-phase motor has a rotating magnetic field, and therefore it'll naturally want to start turning. Where single-phase motors are actually a little difficult to get running, because you just have, with a single phase motor, you just have an up and a down, and there's nothing to kind of start it turning. And so you have to build the motor with some sort of mechanism to get it to start turning. Once it starts turning, it'll turn fine. But a lot of times, if you don't have some mechanism to start it, and you had like your magnet was just perpendicular here, your rotating magnet inside the electric motor was exactly perpendicular to the coil. In a single phase motor, there would be nothing to get it turning. You would have to actually do something to get that turning. And then once you got it turning, it would have enough that the inertia would carry it through that, and then it would push it off as it was at an angle. But with a three-phase system, the electric motor will have a rotating magnetic field, and it'll just start rotating naturally. So those are the reasons why three-phase systems are used all over the place, because again, with one extra wire you can basically triple your power, and you also, with a three-phase motor, is just going to naturally start to rotate.